key distinguished speakers. Our next distinguished speaker is Professor Heng Ji, who from Department of Computer Science at University of Illinois at Urbana-Champaign. She's also an Amazon scholar, and her main research interest is basically in NLP, multimedia, multilingual information extraction, knowledge-based population, and knowledge-driven extraction specifically. So she has many basically awards and prolific resume to list all, but I pick a few. Basically, she was selected as Young Scientist and a member of Global Future Council on the Future of Computing by the World Economic Forum in 2016 and 17. She has also received basically and this recognized in AI's 10 to Watch by IEEE Intelligent Systems in 2013, NSF Career Award in 2009, Google Research Award in 2009 and 14, IBM Watson Faculty Award a couple of times, Bosch Research Award, and multiple Best Paper Award, and has co-chaired NLP related conferences. So without further ado, I hand it over to you, Professor Heng Ji, for your talk.
Thanks so much, Hamid, and thanks, Ben, and all the organizers for this great workshop. So let me share my screen. It's my great honor to talk about this new project that we just kicked off last September by NSF AI Institute on molecular synthesis. So I don't want to pretend to be a chemist or expert in this domain because I have been only learning some basic knowledge for less than a year. And when I was high school student, I really don't like chemistry. So this picture pretty much says what I was like when I was a high school student. I just didn't like it because there are so many things to remember. But this area is really exciting application domain for us to apply document intelligence techniques. So the work I'm going to talk about was done by my postdoc, Dr. Hongwei Wang, and PG students Carl Edwards, Xuan Zhang, Tun Lai, Chen Kai-sun, and my undergraduate student, Weijiang Li. And it's based on collaboration with Professor Jiawei Han from UIUC and Kyung Chiu from NYU. So what I would like to discuss is what exactly is inside the chemical entity. And the motivation is very clear because we just have too many papers. It's impossible to read them. For example, even just for COVID-related papers, across 3 months, we already have about 140,000 papers. And our capability of to read papers is not increasing over time. Every year, at most, we can read about 264 papers. And these two curves I'm showing you the number of papers increasing in Medline, which is PubMed database, and also COVID papers. So that's one problem. The other problem is that because of the overwhelming amount of papers, scientists cannot find all the possible candidates. They don't have time to try that many experiments. For example, for Suzuki coupling, it's a special type of coupling. These are the top 20 candidates that scientists manually picked after many years of work. And if you look at all the possible candidates in the products, there are actually more than 500,000 possible reactions, which means we have no idea how much important information we have missed if we only look into these top 20 candidates. So as an AI community, especially in NLP, we have this community called BioNLP. This has been there for more than 15 years. There are many shared tasks that have been set up and many data sets have been released. However, very few papers are about chemistry. And I will show you why NLP tasks for chemistry domain is still quite different from the biomedical domain. So our overall goal here is to be able to convert the unstructured data to structured knowledge. And there are 3 unique challenges for this domain. The first one is that every entity is not well represented by the natural language context, because the entity has its own graph structures, have its own properties, and these kind of properties and structures are not represented by unstructured context. So that means we need to incorporate the graph structures and their external properties from maybe external ontology and the existing databases to represent each entity. And the second challenge is that a lot of the sentences in literature, especially in chemistry literature, they are very complicated. They involve very complex structures. So if we are doing relation or event extraction, we will need to look into the wide context and capture the global knowledge. And then the third challenge is more interesting because when scientists try to write papers, they don't bother to define any of these entities because they assume the readers are also scientists. So we need to enrich the knowledge representation by combining the external knowledge and then the local context together. And then after we get this kind of multimedia knowledge base constructed, we can apply that to many downstream applications such as retrieval, summarization, and even reaction prediction. So I'm going to talk about our solutions to tackle these three challenges, and then I will be talking about some applications using the constructed multimedia knowledge base. So the first challenge is what exactly is a chemical entity? So this is just one typical example of an entity mention that you normally will see in a sentence in the paper. So the sentence says something to this entity is a biologically crucial reaction relevant to something. So it's only saying it's possibly a candidate entity, but the real properties of this candidate entity is actually reflected in its own graph structure. For example, this dihydroxy means there are two HO links. As indo means there's this special two graphs put together, and then this acid means this structure. So if we only look at character embeddings or maybe BERT embedding, we won't be able to capture all these kind of rich structures and the important knowledge about this entity. And also, as I said, the original sentence in the paper will not have a detailed definition because there are so many entities mentioned and scientists just don't bother to define them again in the paper. So what we need to do is basically look it up in external databases and then try to get this additional sentence which define this entity. And this sentence also includes a lot more knowledge about this entity. So this is very common, especially in chemistry domain, because most of these chemical entities, they are often formula-like names like this, and many chemicals simply don't have any canonical form in natural language yet. In addition, we also should look at all the properties of these chemical entities because the graph structure itself does not capture properties like molecular weight and exact mass. So these property values are very important for us to represent the meaning of this entity. So our idea is to be able to take advantage of this kind of graph structure, and then we are going to initialize the node in this kind of graph using typical contourized embedding, and then we propagate the representation from the neighbors to every current node. For example, for this node, we are going to borrow the representation from their neighbors and then propagate the messages over this graph. After this aggregation, we can then read out the embedding for the whole molecular graph. So that's about graph structure-based embedding. And we also can take advantage of the reaction formulas. So in our embedding composition in a typical natural language task, we can look into things like Microsoft plus CEO equals to John Smith, for example. So that kind of a composition is still very approximate, which means the embedding composition won't give you the exact answer. But the advantage of doing this kind of embedding composition in chemistry domain is because the reaction output is usually the accurate product you will get from the input. So for example, from these two inputs, we are quite sure the output will look like this. So that means if we have many formulas that include this as a product, we can use that reaction formula as another additional contact to represent this entity. So which means we are going to map the reaction space to molecule embedding space directly. For example, we have A plus B produce C and D. We are going to map that into the embedding space. And every G here is encoding results from the molecular graphs propagation that I just mentioned. So that's the first challenge. And then the second challenge is that many sentences include very rich entities and events, and also how these entities are involved in these events, but usually the event trigger and the entity are quite far away from each other. For example, here, CTF and the trigger changes are really far away. So if we only use local counterless embedding, we won't be able to capture the semantic role this entity played in this event. And we want to be able to know the type of these entities are proteins just by looking at their local embeddings. So the idea here is let's try to do anti-linking, link these mentions to external knowledge bases and ontologies, and hopefully the external knowledge base can give us better definition and additional properties and how these entities are reacting or how they are interacting with each other in the external knowledge base. So to do anti-linking, we decided to use a very simple, very efficient CN architecture instead of BERT models, just because for many cases, we can get similar performance even just using very simple architecture. So we do that for every mention in the literature. So for example, here, this mention is linked to this entity in the external database. And then from the external database, we can encode this natural language sentence that describe this entity and merge that together with this sentence from the literature as an additional contact. So we also notice that in the external knowledge base, we often can see additional interaction relations. For example, here we will have trouble to determine the type for FKBP12 as a peptide or protein. But if you look at the interactions between this entity and the FK506 in the background knowledge graph, we can see that they are always interacting. That indicates the type of this FKBP12 in this sentence, in this local context, should be a protein instead of a or peptide. And also, we can look at the database also tell us the semantic type and the definition and the gene entity ID, so that we can further use that kind of information to enrich the input text. So the idea is that once we have this multimodal embedding with the external knowledge enriched representation, then we can try to extract information from unstructured data. So we are going to start by constructing initial span graph by looking at every possible candidate's mentions and consider every pair of entity mentions will have a potential relational events. And then we use the enriched representation to merge the input initial span graph and all the graph structures we can acquire from the external knowledge base. And then after we build these two graphs, we will soft align the mentions and also their relations using attention mechanism. Basically, if they are close to each other, we'll consider the triplet is aligned with the triplet we get from the external knowledge base. So that's the second challenge. And the third challenge is that after we have the richer representation for every entity, we still cannot capture some relations or event arguments because the content is just too complex. So here, just one typical example showing you that the argument FOXP3 appears at the beginning of the sentence, and the localization event, the trigger word, appears at almost at the end of the sentence. And we look at the average distance between trigger and the argument in this GNIR, which is the scientific literature corpus, it's about 0.33 sentence. And in the typical news corpus, we usually only have about 0.21 sentence distance. And the maximal distance can be up to 77 words. So if we only use localized embedding, we won't be able to figure out which content words among the 77 words is used for identifying events and relations. So our idea here is to convert this input sentence into a semantic graph structure using semantic parsing. So the semantic parser we are using here is AMR parser, abstract mean representation parser, because the training data for that parser includes a scientific literature section, and also compared to semantic labeling or dependence parsing, AMR parsing defined many more types of relations. So we train the parser from that special literature section, and then we apply that to every sentence so that we can see the sentence is converted into a graph. And now we have this graph, then we can do graph encoding and graph decoding. So instead of doing sequence encoding, graph decoding, we are doing graph encoding and graph decoding. So basically for every sentence, in addition to the sentence level knowledge graph, we are going to fuse that with the AMR graph so that we can have an enriched semantic graph. And then again, do message parsing to update the representation of every candidate entities. And then finally, we can identify the relations and events and the event arguments. So here, just showing you some results for the shared tasks for entity and the relation ingestion. We can see we get a better performance than all the SOTAP methods that are only using BERT type of embeddings. And this is the event ingestion results. And again, compared to the sequence baselines, we get a better performance. And I would like to show some concrete examples. So here shows this this trigger bind and the entity CII, they are really far away, right? So bind is here and CII is here. So the baseline for that model based on BERT embedding failed to identify the link between, but our model successfully find this semantic role connecting this trigger and this entity. And then the external knowledge graph, the properties help us recognize the thing, the role of this CII is a thing of the transcription event, because that kind of relation or semantic roles are being described in the properties. Similarly, here we, in the baseline model, fail to identify the correct arguments for two binding events in the sentence, because usually in news articles, we don't use one event to serve as an argument for another event. But using the AMR graph structure and external knowledge, we're able to identify the positive regulation effect on this entity. Okay, so by doing this, we are able to construct knowledge base from scientific literature. And then I would like to talk about several applications. The first interesting application I'm personally very excited about is to predict reactions. So if you think about the possible candidate reactions, there are about 500,000 reactions based on the existing molecular entities. So it's almost impossible for any scientist to exhaustively try all these candidates. It would be really nice if we can predict which one has a higher priority than the other. So our basic idea is to first convert the graph structures. Usually it comes as a small string into a graph. And then we are using graph neural networks, which had many different algorithms. I will show the comparison later, to encode this molecular graph using the graph structure and using the reaction formula as a global content. So basically for training, we are going to pairwise R and P, which represent reactant graph embedding and then the product graph embedding. So A plus B equals to C, then A and B will be the input and then the C will be the product graph. And then we found that if we simply minimize the distance between every pair, it's not enough because the training data is lacking of negative examples. So we decided to introduce negative examples as a way to learn contrastive loss. So for every mini batch of the data, we are going to introduce some negative examples. And then the loss of each mini batch becomes the mean of positive loss and the mean of negative loss. So for doing the reaction prediction, we'll take this query. So we consider every reactant as a query. And then we look at all the 500,000 candidates in the data set. And then we try to rank them based on the similarity and based on this contrastive loss. And then if we look at the results comparing with the sequence flat models, we'll get a much better performance. And the interesting thing here is that TAG, this topology-based graph neural network algorithm, achieved a slightly better performance than any of the other graph neural network algorithms, especially like graph attention network, which is usually their best choice for other NLP tasks. The reason is because their graph structures in every reaction are usually quite complicated. So if you look into the topology structure very carefully, that can usually help us assign different weights for different neighbors and can capture the representation better. So the encouraging results is that if we look at the top 10 of the prediction, we're able to cover almost about 92% of the results accurately. So that means instead of looking at 500,000 candidates, scientists can just simply check this top 10 and they are likely to get the best reaction. So in addition to the reaction prediction, we are also interested in seeing whether we can predict properties. So the idea is to look at all the molecules in this data set, and then we put it at the embedding representation for these candidates, and then we apply this to all kinds of classification or regression tasks to predict the properties. So here, just showing you the 3 types of different properties. For example, this one simply says this molecular entity is related to HIV. And we are able to predict these properties very accurately as well. So compared to molecular to VEC, it's a flat model. We get much better accuracy for all the 3 types of properties. And we also try to visualize the results. So here you can see that these blue ones usually indicate small molecules, and these brown ones in the bottom usually indicate the large molecules after we use the graph embedding representation. And this visualization shows we can also capture the property to show this entity is permeable or not. By the way, I have to admit, I have no idea what the permeable means, but I'm still learning. But you can see that these 2 clusters are separated far away in this space. And here shows that when we look at the structure similarity to a particular entity, you can see that the entities similar to this one are all belonging to similar clusters. And those very different ones are belonging to this cluster. And we are also interested in looking at the size of rings, because that's very useful information when we are looking at the properties. So this cluster includes the molecules that have no rings, and these clusters include the molecules that have 1 ring. So that's great because we can predict molecular structures, and we can also rank the reactions. However, scientists may not just believe our prediction results. Sometimes they also need to go back to literature to find the content or evidence to support our prediction. So one important task to do is to get a natural language query or question and retrieve the corresponding molecules from literature. So the current search engines for chemical literature cannot do this. Usually you type in a natural language query and then they will do keyword matching. They will find the strings written in natural language, or you can type in an image. You can input the image, and it will return the similar images using visual similarity. But there's no system that can do cross-media retrieval. But since we already incorporated the graph structure and the natural language content and the structure properties, we are actually have the great opportunity to build a cross-media common semantic embedding space. So we decided to add the natural language content into this graph structure embedding by building a common semantic space. So the idea is very simple. We simply compute cross-modal attention between the description tokens in the natural language content and then the graph structure. So again, we are trying to learn the contrastive loss because otherwise the whole data set is lacking of negative samples. Here showing you the retrieval accuracy. For example, compared to just simply use MLP, our GCN-based model achieved better performance. And here are some examples in the output. So we not only can find these accurate structures, but we can also see the association rules between the natural language description and the graph substructure also are very informative and they are accurate. So we have constructed a new chemistry information rejection benchmark by defining ontologies. So in our current ontology, we have about 62 different entity types and about 59 different types of events, specifically for chemistry domain. And we annotated a set of papers, fully annotated following this ontology, and we are releasing this data set soon as a new benchmark. In the meanwhile, another important application could be applying this to COVID-19 literature so that scientists can look at our results and can help them, for example, make a decision in drug repurposing. So similarly, we defined a new ontology just for COVID-19 literature, and we also released our open source code system to extract anti-iterations events. So this is one of our ACL papers. And these are some examples about how can we use this kind of a constructed knowledge base. So here I'm showing that if we have question about whether this drug has any side effect on COVID, but because of the lacking of experiments, we may not be able to rank them. But if we look at all the other symptoms that are related to COVID, and if you look at the previous disease connecting with the drugs, we can look at all these subgraphs and multiple paths connecting them. Then scientists and doctors can check this subgraph and try to figure out whether these symptoms are severe enough and why that caused. And then they can maybe use this as a way to help them make a decision for rank the priority of these drugs. And because of the cross-media embedding space, we are also able to visualize our constructed knowledge graph using the molecular structures. So the knowledge graph become multimodal. And this makes the results much more explainable. So to conclude, I think this is a very exciting domain. So basically, in the past, we were looking at like, I don't know, natural disasters or human disasters, and try to figure out the terrorist went to which place. So we have been studying that kind of domain for a long time using our information injection techniques. And now I think the techniques and the way to represent the semantics are mature enough so that we can apply them to help ourselves, right? So scientists, they really need help to speed up their scientific discovery. And the fine-grained information injection is just one possible technique that we can use for helping the downstream applications. So in my talk, I showed you the possible applications to reaction prediction and also drug repurposing report generation and also question answering. But we can also use that maybe for query-guided summarization. So right now, the major bottleneck is that I personally feel like the biggest bottleneck for me is I cannot understand my results, right? So I'm lacking of knowledge to understand the errors or what the good numbers mean, right? So we really need to closely work with domain experts and then maybe try to figure out which part of the knowledge or the resources we can incorporate into our representation. And then we need to figure out some effective way to integrate this kind of symbolic domain knowledge with our distributional semantic embedding representations, so that this knowledge empowered representation can be very useful for extraction or any other applications. And the other interesting thing that we have not got any results, but we have already started doing, is to look at the procedural knowledge, because usually every chemistry paper will have a very big appendix that is showing step by step about how they did the experiments, so that other people can duplicate the experiments. But usually in their shared tasks or NLP tasks, we ignore those kind of appendix. But that kind of information is very important to help scientists to design their next experiment. So one ongoing work we are doing is doing schema induction by trying to learn the procedural knowledge. So next time when they have new setting or new set of variables or conditions, we can predict how to do the step-by-step experiments. And also, if we simply publish another NLP paper, increase F-score, it's not useful for scientists, right? So we need to do a lot more low-level dirty engineering to put things together into a platform. And currently in the chemistry community, they don't have anything like that. So a lot of things look quite basic to us. For example, how to index the multimodal representation, and how to do the literature retrieval, and how to summarize the results using abstractive summarization. So we are now in the process of building these things together, so that they can keep giving us feedback, and then we can use the feedback and the additional resource to improve our components. And like I said at the beginning, I really hated chemistry when I was a high school student, and now I really like it. I kind of really like the learning process. So there are so many amazing things happening, and a lot of the results are very useful. So in our center, we are doing this very basic, like chemistry 101 kind of tutorials. So I have been learning a lot. So this is a picture actually showing that this chemistry professor was testing my knowledge. Yeah, so that's it. Just want to welcome more people to join this exciting domain. Yeah.
Thanks, Heng. Actually, a very inspiring story about actually, having a perspective about chemistry and now going on the opposite side of the spectrum, loving chemistry. So let's open up the floor for questions. Any questions, please raise your hands and open up your mic.
I'll start with a very naive question. So it looks like the stability of chemical reaction plus the consistent way that scientists write in language to describe them makes it so that synthesizing the training example is simple or straightforward in this domain. Do I understand it correctly, or I'm too naive?
Yeah, I mean, that's my intuition as well. I mean, I didn't do any theoretical comparison with, for example, what we normally do in, like knowledge graph completion, relation predictions, right? But I think intuitively, embedding composition in this simple way, like adding things together, like this actually makes more sense for chemistry domain. Because if you think about semantic relation extraction, right? Like, for example, if I want to extract employee relation, then UIUC minus Heng Ji does not equal to Microsoft minus Ben Han, right? Or Han. Yeah. So it's just an approximation, right? But in chemistry domain, we actually have millions of this kind of formulas. So this actually gives us great opportunity to really take advantage of it. Yeah.
So the data is not a problem to you?
I think the 500,000 is enough for this these two tasks that we are doing experiments, because if you look at the, I don't know, like top 10, it's quite good, right? But of course, top 1, we're still missing a lot, right? But this already helped rank these 500,000 samples. So about data set, these data sets, these formulas are publicly available, but there are many other very highly valuable reactions are not publicly available. And we have been talking to many publishers, journal databases. I don't want to mention their name because it didn't work out. They often charge us a lot of money to give us data, and we are not allowed to publish any results using their data. So basically, they have the whole copyright of the data set and any results published on top of it. So we decided not to pursue that path, but they usually own a lot more reactions than this kind of public data set. So I think if we can figure out a way really to convince them, share it in a more, how to say this, scientific way. I mean, I personally don't, I'm not buying that why, we publish a paper in some journal, another journal should own the data, right? I mean, I don't understand that logic, but that's what's happening. So I think we need a community effort really convince them it's a valuable way to just share things publicly, or maybe even just lower down the cost would be great. Yeah.
Thank you.
Okay, thank you. I think we have time for one more question. Linwei Li, you may unmute yourself and go ahead.
Hi. Yeah, that was a great talk. I'm kind of curious about. So at first we are talking about we have event extraction, like entity extractions and the relation extractions, and we kind of generate embeddings for them, and we also, and the second task or the third task is reaction predictions and stuff. So I'm just wondering about so are the embeddings used the same for these two tasks? So basically it's like BERT, and we use the same encoders to generate the embeddings for the chemical entities, and then it's just that the downstream tasks are different, or they kind of currently they are kind of totally separate pipelines. So
the information ingestions framework used all of the embeddings I mentioned. So it used the graph structure. So use this graph structure, and then the definition sentence and properties, relations in the external knowledge base, and combined with the original input natural language text. So the entity relation event ingestion basically use everything. Reaction prediction, we are only using the graph structure and the initialization of molecular to vec embedding. So for the reaction prediction, we are not using the natural language content yet. So that will be our next future work. So and then the other one, the cross-modal retrieval, this one also used all the embedding representations that I talked about.
Okay, so do you believe that it kind of can become a kind of universal embeddings generation, yes. Like the pipeline?
Yeah. Because actually, if you look at the results comparing to BERT, right? So we tried science BERT and bio BERT. So the final one is just use that kind of flat model. You can see the performance for property prediction is not as good as this kind of graph model, even though the graph embedding is learned from a much smaller data set. Yeah, so indeed the goal is to be able to combine all these resources and release embedding for the whole community to use. Yeah. I cannot claim it's universal because we don't have all the data sets, but I'm hoping to have that platform set up soon so that we can collect papers on a daily basis and then keep updating the embedding. Yeah.
Thank you. Maybe a quick, last question. So I was wondering, I'm not an expert in this area, but when I was looking at the formula drawings, and I was wondering if image-based basically as a feature in the embedding would make a difference. It seems most of what you talked about was about graph level, more graph-based embedding.
Yeah, so my best understanding after I worked with this chemist is they actually have standard tools to draw images. I mean, for example, they won't use, just Photoshop or any, like, the tools we use, right? So they have their special tools, and which means that the tool can keep tracking of each line or each node, so that different color has different meaning and different shape have different meaning. So we didn't see that as a problem. So basically, if someone upload the image, converting that image to a graph is very simple, and it's usually accurate.
I see. Okay.
Yeah.
Thank you again, Professor Heng Ji, for the great presentation. And I invite everybody else who might have their questions to directly approach or keep your question for the panel, which is upcoming.